Good morning, all of you. Welcome to Jay in the Rank Zone. So, we have completed two lectures in hydrogen compounds. Now, we are going to discuss lecture 3, that is water in hydrogen compounds. It's very, very important. So, please listen carefully, all of you. So, let us start now. Water. So, we have completed already first lecture and second lecture. Hydrogen, dihydrogen preparation properties and uses. Now, in this lecture, we are going to start water and we will try to finish off it in this lecture only. Let us start now. So water is an important hydrate of oxygen, which is principal about 75% principal constituent of Earth's surface. Already we know 3/4 of Earth is surrounded with water only. 3/4 part of Earth is surrounded with water. So it is most abundant, omnipresent, and easily obtainable of all chemical compounds. It is a significant component of animal as well as vegetable matter and they play a vital role in their process. It ranks next to oxygen in the importance of our existence. It constitutes about 65% of human body and about 95% by weight of some plants. It can be easily transformed from liquid to solid or solid from liquid to gaseous state and vice versa. So easily we can convert solid to liquid, liquid to gas in case of water only. So this is about the introduction of water. So let us see now. Now distribution of water. The distribution of water over the Earth's surface is not uniform. The desert regions have no permanent surface water, while the oceans cover about 78% of the Earth's surface. They contain 97% of the available water. So out of the total surface, only 2.7% is fresh water and rest is locked and in polar ice caps, glaciers are under the ground and is not readily available. So this is the abundance of water on the Earth's crust. Next, so in water is the shape of water molecule. It is angular in shape, and in this it undergoes oxygen undergoes sp3 hybridization. Oxygen undergoes what hybridization? sp3 hybridization. sp3 hybridization. The shape of water molecule is angular in nature. Bond angle is 105 degrees and it contains two lone pairs. It contains how many lone pairs? Two lone pairs and two bond pairs. So that's why it is making total 4. So that's why it is undergoing sp3 hybridization. So this is the shape of water molecule. In water molecule, oxygen atom contains two lone pairs. It contains how many lone pairs? Two lone pairs and two bond pairs. Next continuation. So polar nature of water. OH bond causes the molecule to behave as permanent electric dipole. The OH bond in water causes the molecule to behave as permanent electric dipole. The dipole moment of water molecule has been found to be 1.84 device, which confirms its polar nature. So the OH bonds in water, so hydrogen bond, this is hydrogen bonding. So in water, two types of bonds are present. One is OH bond and there is hydrogen bonding. Hydrogen bonding, due to the hydrogen bonding only, the boiling point of water is 100 degrees C. The boiling point of water is 100 degrees C due to hydrogen bonding only. So because of hydrogen bonding only, the boiling point of water is 100 degrees C. So this dotted line represents hydrogen bonding and this strong line represents OH bond. So due to the presence of OH bond causes the molecule OH bond causes the molecule to behave as permanent electrical dipole. So OH bond behaves as permanent electrical dipole. So there exists a dipole moment. So the dipole moment is nothing but from hydrogen, the electrons are going towards what oxygen atom. So for example, if we take this oxygen and hydrogen, so there exists a dipole from hydrogen atom to oxygen atom, and these two are opposite in nature. So that's why the net dipole moment mu is equal to for water, net dipole moment mu is equal to 1.84 device. So this is called water introduction. Next continuation. Next, aggregation of water molecules. In gaseous state, the individual covalent molecules, this is also very important concept, aggregation of water molecules. In gaseous state, the individual covalent molecules H2O exist as such. However, in liquid state, large aggregates of H2O units are formed because of their association to intermolecular hydrogen bonding. Due to intermolecular hydrogen bonding, the water will form so many, the liquid in liquid state water forms large aggregates. Large aggregates means, what is the meaning of large aggregates? It means water is forming, so many water molecules can form together, join together to form aggregate. The intermolecular hydrogen bonding is responsible for the abnormally high freezing point, boiling point, heat of fusion, and heat of vaporization as compared to the hydrates of other elements of oxygen family. So, other elements of oxygen family means like hydrogen sulfide, phosphine, etc. So, the extent of association, however, depends upon the conditions of temperature and pressure. In ice, a solid state of water, each water molecule is tetrahedrally, please note down this point, is tetrahedrally surrounded by four neighboring water molecules with their oxygen atoms occupying the corners of tetrahedron. So there are four hydrogen atoms around each oxygen atom. The two of the four hydrogen atoms are bonded by covalent bonds. In ice, we are discussing about ice. So bond length is 100 picometers, whereas the other two are linked to hydrogen bonds 176 picometers as shown in the figure. This gives highly three-dimensional structure having large vacant spaces which may be compared to open cage. So the solid form of ice will be looking like open cage. Open cage, very, very important. So please make a note of all these things. So let us see the diagram now. So due to open cage structure, open cage like structure, ice has a relatively larger volume for a given mass of liquid water. So if you see, compare the volume of water and volume of ice, the volume of ice is larger when compared to volume of water because of open cage like structure. Consequently, the density of ice is less than that of water. As volume increases, density decreases because density is proportional to 1 by V. Since density is proportional to 1 by E, 1 by V, as the volume of the ice increases, so naturally its density is decreases than water. That's why it floats over water. As the temperatures rise beyond 273 kelvins, open cage-like structure dismantling due to cleavage of some H bonds and ice melts. The breaking of H bond causes aggregation of water molecules to have closer, resulting in the decrease in the volume and thereby increasing density. So water has more density than ice. This continues till 277 kelvins when the density becomes maximum. Beyond 277 kelvins and more, hydrogen bonds cleaves and due to expansion of liquid water starts occurring due to increased kinetic energy of molecules and the density again starts decreasing. However, it remains higher than ice. Hence, the density of water is maximum at 277 kelvins, that is 4 degrees C. This is called anomalous expansion of water. What is this called? Anomalous expansion of water. So water is as we from 4 to 0 degrees C, instead of contracting, water gets expanded. This is called anomalous expansion of water. So from 4 degrees to 0 degrees C, instead of contracting, water gets expanded due to anomalous expansion of water. So this point is relatively very important. So please listen carefully, all of you. Next, coming to physical properties of water. Molecular mass of water is 18.015. That's why we'll take it as 18 grams. Melting point is 273.2. That's why we'll take it as 0 kelvins. So 0 degrees C, and boiling point is 373.2. So it is 0 degrees C and 100 degrees C with respect to centigrade. And density 0.997. We'll take it as 1. And heat of vaporization is 40.66 kilojoules and heat of fusion is 6.01 kilojoules. Specific heat is 4.11177. So these are the physical properties of water. Next continuation. Now coming to chemical properties of water. Action towards litmus. Pure water is neutral to litmus. Pure water is neutral. So water is neutral. As we already know, it has no effect on litmus paper. Neither it converts the litmus paper to blue or red color. Water is quite stable and does not dissociate at high temperature. The dissociation into its elements is only 0.0002% even at 1500 Kelvin C. So that's why water is quite stable. The small conductivity of pure water reveals its dissociation into H3O plus and OH minus ion. So water dissociates to form H3O plus, that is hydronium ion, plus OH minus ion. Next, acid-base reactions. Water is amphoteric substance because it can act as acid as well as a base. The pH of water is 7 and is neutral towards litmus. Next continuation. Heavy water. So these are about the properties of water. So physical properties of water and chemical properties of water also we have discussed. Amphoteric character. So let us see the amphoteric character of water. Some more amphoteric important reactions of water. So water is an amphoteric in nature. How it can combine with acid as well as base. It can combine with acid as well as base. Let us see now. H2O combines with acid. H2O combines with base, that is ammonia, and forms NH4 plus OH minus. So acid and base. So the autophotolysis, that is self-ionization, may be represented as is the self-ionization of water and ammonia. Similarly, water plus acid. So water behaves as an acid as well as base. And next, water combines with many compounds. Water combines with many compounds to form different compounds here. So next, heavy water. What is heavy water? It is also called as deuterium oxide D2O. Heavy water is oxide of heavy hydrogen deuterium and is also called deuterium oxide. So the isotope of hydrogen deuterium along with oxygen is called as heavy water. It is represented by the formula D2O R2H2O. So the credit of discovery of heavy water goes to Uwe, who first proved that 6,000 parts of ordinary water contains 1 part of heavy water. So in ordinary water, 1 ppm, the occupancy of heavy water is 1 ppm is present, that is parts per million. So the Lewis and Donald in 1933 were able to isolate few ml of heavy water by the prolonged electrolysis of alkaline water. Alkaline means water with some base. It's called alkaline water. So preparation of heavy water. The main source of heavy water is an ordinary water from which it is prepared either by prolonged electrolysis or by fractional distillation. Let us see the prolonged electrolysis of heavy water will give you deuterium oxide. So prolonged electrolysis of water. In this method involves multi-stage electrolysis of ordinary water containing. So first you have to take ordinary water along with sodium hydroxide. The cell used for electrolysis. So ordinary water containing sodium hydroxide. The cell used for electrolysis was designed by Brown, Daggett, and Uwe. It is a cylindrical vessel made up of steel which acts as cathode. So the cylindrical steel cathode. This is called steel cathode, and the anode is perforated cylindrical sheet which is made up of nickel. So nickel is anode. The electrolysis is carried out in different stages as described below. In actual practice, large number of electrolysis are used. So this is called prolonged electrolysis of heavy water, ordinary water, alkaline, ordinary water. First stage. In this stage, 30 electrolytic cells, see how much big process it is. 30 electrolytic cells are used. Each cell is filled with about 3% solution of sodium hydroxide. The electrolysis is carried out about for 72 hours using a current of 110 volts. The volume reduces to 1 by 6th of the original volume taken. So the volume reduces to 1 by 6 of the original volume taken. So the electrolysis is carried out about for 72 hours using a current of 110 volts. So the volume reduces to about 1 by 6th of original volume taken. So 1 by 6th of original volume taken. This stage involves second stage. This stage involves the electrolysis of residue left from the first stage using 6 electrolytic cells. So in second stage, how many electrolytic cells we are supposed to use? 6 electrolytic cells. The gases evolved are burnt and water is formed to return to the first stage cell. The residual liquid contains about 12% of heavy water. So third stage, this involves the electrolysis of residue of second stage. The content of heavy water is raised about to 60 degrees. The gases evolved are burnt to get water that is fed to second stage cells. So in this third stage, what happens? The electrolysis of residue of second stage will be done. The content of heavy water is raised about 60%. So from 12% it is raised to 60%. The gases evolved are burnt to get water that is fed into second stage cells. Continuation. This stage involves the electrolysis of 99%. So electrolysis of residue of third stage and here. So prolonged electrolysis in each and every state, in each and every stage, we have to do electrolysis, means by passing current. So nearly 99% of heavy water is obtained. The gases evolved are burnt in the second stage. So 99% of in this fourth stage, 99% of heavy water is obtained. The gases evolved are burned as usual and sent to third stage cells. Fifth stage, the 99% heavy water from fourth stage is made free from alkali and other impurities by distillation. And distillate is electrolysis. Fifth stage, we have to do fractional distillation. Here, the gas evolved are D2 and O2 which are burned to get 100% pure heavy water. Pure water. So in this way, heavy water is formed. So it's only small percentage. So this is finally fractional distillation. In this method involves partial separation of heavy water from ordinary water because the boiling point of heavy water is quite higher than ordinary water. So advantage is that taken of the small difference in the boiling point. So how can we do distillation? Based on the difference between the boiling point of protium oxide, that is normal water, is equal to 373.2 kelvins, and deuterium oxide, which is equal to 374.3 kelvins. Slight difference. Since the difference in boiling point is very small, a long fractionating column about 13 meters is used for distillation and the process is repeated several times. The lighter fraction, the lighter fraction due to water is distilled first, while heavier fraction D2O is left behind. The heavier fraction becomes rich in D2O. Because since boiling point of normal protium oxide, that is water, protium oxide is what? Water. So is less when compared to deuterium oxide, slightly less. Due to this difference, deuterium oxide is left in the container only. So this is called fractional distillation. What is this called? Fractional distillation of ordinary water. Next, we have hard water and soft water. This is very, very important. Preparation of water is not that much important, but when you compare to hard water and soft water, it's most important. What makes the water very hard? So water is classified into categories depending upon its behavior towards soap solution. These are soft water and hard water mainly. So based on the behavior towards soap solution, water is classified into two categories: soft water and hard water. Water which produces lather with soap solution readily is called soft water. Water which produces lather with soap solution is readily is called soft water. Distilled water and rainwater are common examples of soft water. So distilled water and rainwater. Next, hard water. Water which does not produce lather with soap solution easily is called hard water. So example, sea water, tap water are common examples of hard water. So now we are going to see what makes the water hard. So what makes the ordinary water hard, that we are going to see. From that it is very, very important. So please listen carefully, all of you. So causes of hardness of water. Hardness of water is due to the dissolved impurities. See here, this is what makes water hard, due to the dissolved impurities of the salts of like bicarbonates, chlorides and sulfates of calcium and magnesium. So due to the presence of salts of, that is what type of salts of calcium and magnesium, magnesium carbonate, sorry, magnesium bicarbonate, calcium bicarbonate, magnesium chloride, calcium chloride, magnesium sulfate, calcium sulfate. So due to the presence of these salts, that is salts like bicarbonates, chlorides and sulfates of calcium and magnesium, water becomes hard. Water gets contaminated by these salts when it passes through the ground and rocks. Hard water does not produce lather with soap solution readily because the cations, that is calcium and magnesium present in hard water, react with soap, which is a mixture of sodium salts of fatty acids like stearic acid, palmitic acid, oleic acid, etc., to form a precipitate of calcium and magnesium salt of fatty acids. So why this hard water is not giving lather with soap? Because in hard water, due to the presence of salts of calcium and magnesium, they combined with soaps. What is soap? Soap is nothing but it is a mixture of sodium salts of fatty acid. Sodium salt of fatty acid is called soap. So present in hard water react with soap, which is mixture of sodium salts of higher fatty acids like stearic acid, palmitic acid, oleic acid, etc., to form a precipitate. So they combine with soap and forms precipitate of calcium and magnesium salt of fatty acids. Due to which what happens? The hard water does not give lather with soap. Thus, no lather is produced until all the calcium and magnesium ions have been precipitated. This leads to the consumption and hence wastage of lot of soap. So, hard water is therefore not fit for washing purposes and even not fit for drinking also. So, what makes water hard? Due to the presence of salts of calcium and magnesium. Due to the presence of salts of calcium and magnesium, water is very hard. Ordinary water, so hard water. So, which causes temporary hardness, which causes permanent hardness, also we'll discuss now. Let us see. So, the hardness of water is of two types mainly. First one is temporary hardness and permanent hardness. So, what is temporary hardness? So, it is due to the presence of soluble bicarbonates of calcium and magnesium. So, only bicarbonates of calcium and magnesium are present that makes water temporary hard. Such water is also said to possess carbonate hardness. So, the term temporary indicates that most of the hardness can be removed just by simply boiling the water. Very, very important. That's why we'll use the word temporary hardness. So temporary hardness is nothing but due to the presence of salts of, that is soluble bicarbonates of sodium, calcium bicarbonate and magnesium bicarbonate. And these calcium bicarbonate and magnesium bicarbonate can be removed by simply boiling the water. That's why we'll call it as temporary hardness. The bicarbonates of calcium and magnesium are formed in water by dissolution of carbonates of calcium and magnesium in the presence of atmospheric carbon dioxide. So how these bicarbonates of calcium and magnesium are formed in water? By the dissolution of carbonates of calcium and magnesium in the presence of atmospheric carbon dioxide. So calcium combines with atmospheric carbon dioxide, magnesium combines with atmospheric carbon dioxide, and they form bicarbonates. And these bicarbonates are formed in the water, and these bicarbonates can be removed by simply boiling the water. That's why we call it as temporary hardness of water. So what makes water temporarily hard? It is due to the presence of calcium and magnesium bicarbonate. Next, what is permanent hardness? It is due to the presence of chlorides and sulfates of calcium and magnesium. So if calcium sulfate or calcium chloride, magnesium sulfate or magnesium chloride is present in the water, it makes water permanent hard. Such water is also said to possess non-carbonate hardness. The term permanent hardness indicates the type of hardness cannot be removed by simply boiling of water. We have to use certain chemical methods. So now we are going to discuss about all those methods. Very, very important. Now, softening of hard water. How to do softening of hard water? It can be done by Calgon process. The process of removing metallic ions, calcium and magnesium is responsible for the hardness of water is known as softening of water. So, in all the experiments, our motto is to remove calcium ions and magnesium ions, which are responsible for the hardness of water. Nothing but it is called as softening of water. So, a number of methods are available to soften water depending upon the nature of dissolved mineral salts as described below. So we have so many methods to soften the hard water. Next continuation. First, removal of temporary hardness. First, by boiling simply. Temporary hard water is taken in large boilers and the boiled for about 15 minutes. Consequently, the bicarbonate of calcium and magnesium present in the water decomposed into the soluble carbonates which are settled at the bottom of the tank as precipitate which are removed by filtration and decantation. So in this way, so simply by boiling water, what happens? The calcium bicarbonate and magnesium bicarbonate just converted into calcium carbonate and magnesium carbonate, and they will settle down in the at the base of the furnace, due to which what happens, They can be easily filtered off or by decantation. So this is the way for removal of hardness of water, temporary hardness of water. Next, calcium hydroxide. This is called Kalgan's process. So this is nothing but the calculated amount of calcium hydroxide lime is slaked lime is added to temporary hard water. The soluble bicarbonates are converted into soluble insoluble carbonates, which settle down at the bottom of the tank and are removed by filtration. So this is called Clark's method. So this Clark method, what happens in this Clark method, we have to add calcium hydroxide. That is calculated quantity of lime. That is calcium hydroxide is added to hard water. What makes this one? Only for removal of temporary hardness of water. The soluble bicarbonates are converted into insoluble carbonates. Insoluble carbonates. So, for example, here I write the equation in Clark's method. So, MHCO3 taken twice. That is the where M can be calcium or magnesium, where M is equal to calcium or magnesium. This is treated with calcium hydroxide. So this what happens when small amount of lime is added, they form insoluble precipitate of carbonates, that is MCO3, magnesium carbonate or calcium carbonate, along with water and carbon dioxide, along with water and carbon dioxide, which makes, so if you add calculated amount of calcium hydroxide to this, what you have to add calcium hydroxide, then what happens? It forms M carbonates plus calcium carbonate. So precipitate is of magnesium carbonate and calcium carbonate plus water. No carbon dioxide is formed. So here no carbon dioxide. So please make a note. So this is called Clark's method. In Clark's method, what is happened? Uh, for hard water, small amount of calcium hydroxide, calculated quantity of lime is added, due to which what happens? It forms insoluble metallic carbonates along with water. This insoluble precipitate is been removed and filtered off by the means of filtration. So in this way, so we have two methods of removal of hardness of water. First one is by boiling. Second one is by Clark's method. In Clark's method, we have to add a calculated quantity of lime is added to temporary hard water. So the soluble bicarbonates are converted into insoluble carbonates and which are present, which will settle at the bottom of the tank and are removed by filtration. Next, removal of permanent of hardness of water is very, very important because from this you'll get a questions. So how to remove permanent hardness of water? Let us discuss now. Permanent hardness of water can be removed by the following methods. First, by chemical additives, that is addition of washing soda. In this method, calcium ions and magnesium ions can be. So main motto is to remove calcium and magnesium ions. So in this method, by the addition of washing soda, first method. In this method, calcium and magnesium ions can be precipitated by the addition of calculated amount of washing soda. Washing soda. So when this washing soda, what happens? Calcium ions or magnesium ions along with the carbon ions combines together to form MCO3 carbonate. It's called what? MCO3. Precipitated by the addition of washing soda, then it forms carbonate, insoluble carbonate. So what is the formula of washing soda? Washing soda is sodium carbonate dot 10H2O. Sodium carbonate dot 10 water molecules. Sodium carbonate along with 10 water molecules is called as washing soda, or even sodium sulfate also you can add. Next, second method. So this is first method. So in this method, calcium ions and magnesium ions can be precipitated by the addition of calculated amount of washing soda, that is sodium carbonate along with water. So this washing soda combines with M plus 2 ions and forms MCO3 precipitates, that is insoluble precipitate. Next, continuation. So removing of permanent hardness of water is most important. Next, Kalgan's method, very, very important. This is called Kalgan's process, very, very important. In Kalgan's method, in this method, addition of sodium polymetaphosphate, Kalgan, is added. So what is this called? Kalgan. So in this method, calcium ions and magnesium ions are rendered ineffective by the addition of sodium polymetaphosphate, Na3PO4. So what is sodium metapolyphosphate? The formula is sodium metapolyphosphate. It is nothing but what? It is Na3, Na2, Na4. So it is nothing but NaPO taken 3 times X. NaPO3 taken 6 times. Usually it is nothing but NaPO3 taken 6 times. Very, very important. So this is called sodium polymetaphosphate. Poly means so many. The trade name of which is meaning called calgon, means calcium gone. Very, very important. Calgon means what? Calcium gone. Calgon is represented by sodium hexametaphosphate, as I told you, NaPO3 taken 6 times. Calcium and magnesium ions of hard water reacts with calgon to form soluble complexes. The complexes of calcium and magnesium so formed remain dissolved in water, but they do not cause hindrance in the formation of lather. This is because calcium and magnesium ions are not free to react with soap, but these have been tied up in stable complexes. This is also known as sequestration of calcium and magnesium ions. Sequestration of calcium and magnesium ions. What happens here? You can see here. So when calgon is added to hard water, the calcium ions and magnesium ions present in it combine with sodium phosphate, sodium polyphosphate, that is calgon, to form soluble complex of calcium and magnesium salts. They form soluble complex of calcium and magnesium salts. So let us see the equation now. 2 moles of MCl2, where M can be calcium or magnesium, combines with sodium metahexaphosphate. Sodium hexametaphosphate can be taken as Na2 outside, Na4 PO3 taken 6 times inside. This is the complex compound. This is called calgon. This is called what? Calgon means calcium gone or magnesium gone. Combines together to form a complex called, so Na2 M2 M2 PO3 taken 6 times, PO3 taken 6 times. This is complex. This is called complex formed by the calcium and magnesium salts plus 4 molecules of NaCl. Means this 4 Na combines Cl minus 2Cl and forms 4 NaCl. So this is the reaction taking place with calgon. So the complex of calcium and magnesium ions do not form any precipitate with soap and hence readily produce lather with soap and hence produce lather with soap solution. So the complexes of calcium and magnesium so formed. This is the complex of calcium and magnesium formed. Is called the complex of calcium and magnesium so formed. Remain dissolved in water, but they do not cause hindrance in the formation of lather. This is because calcium and magnesium ions are not free to react with soap because they are inside the complex, because they are inside the complex, not free react not to free not free to react with soap, but these have been tied up in stable complexes. So this calcium and magnesium have tied up in stable complexes. This is also known as sequestration of calcium and magnesium ions. So this compound formation is nothing but due to the sequestration of calcium and magnesium ions. So this is the complex formed. So in this way we can remove calcium and magnesium salts from hard water. So this makes water soft. So what is this calgon? Calgon is nothing but sodium hexametaphosphate. What is calgon? Calgon meaning means calcium gone. It is called as sodium hexametaphosphate. The formula of this is NaPO3 taken 6 times, which can be represented as, calgon is best represented as Na2 outside, Na4 PO3 taken 3, PO3 taken 6 times. This is the complex. And this, in place of this Na4, two molecules of metal, that is magnesium or calcium, because the valency of magnesium or calcium is 2, whereas valency of sodium is 1. So that's why two elements, two metals will be replaced here. So in this way, calcium and magnesium is removed from hard water. That is nothing but due to the permanent hardness of water. So this is called calgon method. So in this method, what happens? Calcium ions and magnesium ions are rendered ineffective by the addition of sodium hexametaphosphate. Due to this calgon, what happens? It combines with the calcium and magnesium and forms a stable complex. Forms a stable complex, that is insoluble complex, which is called as sodium magnesium complex or sodium calcium complex along with phosphate. Very, very important. This is called Calgon's method. So please try to understand. It's very simple to understand. Everything has been written carefully here. So easily you can understand and easily you can write in the classwork so that you can understand it better. From this Calgon method, definitely they are going to ask questions in the examination. So in this way, we'll do. Next, degree of hardness of water. So before going to degree of hardness of water, we have one more method that is called Gauss permitted process. What is this called? Gauss permitted process. So we'll discuss Gauss permitted process. After that, we'll go for degree. So still two more methods. So first method we have done. Second method is addition of sodium polymetaphosphate. Now I'm stop sharing this, and here I'm taking a new slide so that for easy for us to understand easily. Then we'll come back to the main slides again. So in this method, what happens? So second method of purification of hard water, that is mole of permanent hardness of water, that is ion exchange method. This is called what? Ion exchange method, or Gauss permitted process. This is also very important. First method, Calgon method. Second method, Gauss permitted process. First we have washing soda. Next we have Calgon method. Third one we have Gauss permitted process, that is also called as ion exchange method, inorganic cation exchanges and organic cation exchanges. So it is permitted method of water softening. So next we have permitted method of ion exchange method, which is nothing but also called as Gauss permitted method process. First one. So let us see. Permitted is an artificial zeolite. So here I'm writing permitted is an artificial permitted is an artificial geolite. Geolites are nothing but what are geolites? This we have discussed already. They have nothing but shape selective catalysts, geolites. So chemically it is nothing but chemically permitted is called chemically it is that is permitted is sodium aluminum orthosilicate. Sodium aluminum sodium aluminum orthosilicate. Sodium aluminum orthosilicate is called permitted. The formula is Na2Al2, that is sodium aluminum orthosilicate Si2O8 dot X water molecules. This is called permitted. So three water molecules. So this Gauss permitted is also represented as represented as Z, also represented as NaAl, that is sodium aluminum SiO4 dot 3H2O. This is called permitted dot 3H2O. This combines with 2 moles of this combines with calcium ions and forms AlSiO4 taken twice dot calcium plus 2 moles of sodium. 2 moles of sodium ions. So this Na2Z is nothing but what? Sodium combined with, so this is called, so sodium ions is been, calcium is absorbed from the hard water by sodium aluminum silicate, that is sodium aluminum orthosilicate. So this is called ion exchange method or Gauss permitted process. So in ion exchange method we have two, that is first one is Gauss permitted method, is also permitted. Permitted is nothing but artificial geolite. It is nothing but shape selective catalyst. So Na2Z, as Z is called Na2Z, that is permitted, combines with MCl2. So finally we can write Na2Z combined with MCl2 forms MZ. MZ means this is AlSO4 taken twice is called Z plus 2 NaCl. So here M is called, where Z is equal to zeolite. Z is equal to zeolite. It is equal to AlSiO4 taken twice. AlSiO4 taken twice is called Z. What is Z here? Again, right? It is equal to Al aluminum silicate. That is nothing but Z. So Na2Z. So that is Na2Al2Si2O8 dot X2O. It's called as Z. So Na2Z, that is permitted sodium zeolite combined with M is equal to here, where M is equal to calcium ions or magnesium ions. So M is equal to calcium or magnesium. So it forms Mz, that is AlSO5 SaO4 taken twice dot Ca plus 2 moles of NaCl, 2 moles of Na plus and Cl minus. So this is called, in this way, magnesium ions and calcium ions are being formed as a soluble complex compound. Soluble complex compound, so that is precipitate, it is formed. So due to which what happens? Hardness is removed. So this is called second method of Gans permitted process. It is also called as Gans permitted process. It is also called as ion exchange method because sodium ions are exchanged with calcium or magnesium ions. In this case, what happens? Sodium ions are exchanged with calcium or magnesium ions. So this is called second method. I hope it is clear. Next continuation. Third method, that is called what as, very, very important. This is also there in the NCERT textbook. Also, you have this, that is called organic ion exchanger. This is called what? Organic ion exchanger. Organic ion exchanger. In this method also, we can make permanent hardness of water soft. So what is this we have to do? So these are complex organic molecules having big molecules with acidic group. So these are giant organic molecules, giant organic molecules, giant organic molecules. This is most preferable method, having with either acidic group or basic group, with either acidic group, that is acidic means like acidic group, in brackets we can write COOH, comma, sulfonic acid, etc., or basic group, that is in bracket we can write ammonium ions or OH minus ions, OH minus or amine ions, NH2 minus. So attached to them, attached to them. So these are called organic ion exchanges attached to them. What are organic ion exchanges? These are giant organic molecules with either acidic group or basic group attached to them. So we have cation exchanges, cation exchanger. In cation exchanger, what happens? Cation exchanges. What is this cation exchanges? This M plus 2 ions, that is calcium or magnesium, where M is equal to calcium or magnesium ions. M plus 2 is equal to, combines with 2 H plus of acid group, H plus of acid group, that is resins. Resin means acid group, H plus ions. It forms M resin taken twice, that is organic compound, giant organic compound, plus 2 H plus ions. So this is called cation exchanger. In cation exchanger, this is taking place. And next we have anion exchanger. Anion exchanger, what happens? Anions of, that is anions, that is chlorides or sulfates, anion exchanger. So what happens here? Cl minus combines with bases, that is OH minus, and forms Cl minus resin plus OH, Cl minus resin plus OH minus. So this is called, even sulfate ions also getting exchanged. Sulfate ions is SO4 2 minus. So here I'm writing sulfate ions, I'll write here separately. So in this way, anions and cations are getting exchanged. Very, very important. You can see why this method is more preferential than all the other methods, because in these, so usually what happens, due to the presence of magnesium chloride or calcium chloride or magnesium sulfate or calcium sulfate, water gets hard. So first, magnesium or calcium is being removed by using cation exchanger. In this, magnesium ions or calcium ions are removed by forming complex. And in these, what happens? Chloride ions or sulfate ions are being removed. So both anions and cations are removed from ordinary water, that hard water. So makes it which makes them very easily soft water. So this method is more refined than all other methods. In this method, what happens? These water containing soft water, water containing calcium and magnesium salts, that is permanent hardness, are treated with giant organic molecules with either acidic group or basic group. Acidic group is acting as cation exchanger and basic group is acting as anion exchanger. So both cations and anions have been exchanged and removed in the form of resins. Resin is a giant organic molecule. So the water obtained by this method is free from all types of cations and anions and is known as deionized water. So the water, whatever the water is obtained by this method is also called as deionized water because both cations and anions are removed. So that's why it is called deionized water. Very, very important. So these are the different methods of these are the different methods of purification of water, hard water. So it is clear now. So let us go back to the slides again. Now I am sharing the slides for you. So let us start now. So this we have already done. Next continuation. So Calgan method is finished. Degree of hardness. Next topic we have degree of hardness of water. So what is degree of hardness of water? So methods of purification of hard water we have done. So purification of hard water is very, very important. Next we have degree of hardness of water. So degree of hardness of water is defined as the number of parts of mass of calcium carbonate equivalent to various calcium and magnesium salts present in 1 million parts by water. 1 billion parts by mass of water. It is expressed in ppm, parts per million. So that is called degree of water. It may be noted that degree of hardness up to 100 to 150 parts per million in water required for our daily needs such as cooking, bathing, washing of clothes, etc. is tolerable. But if degree of hardness exceeds this limit, then water is not suitable for domestic use. So that is what degree of hardness of water. It is nothing but depend as the number of parts of mass of calcium carbonate. So mass of calcium carbonate, what is the mass of calcium carbonate? Calcium is 40 plus carbon is 12, oxygen is 16 into 3, 48. So it is equal to 100 grams. Actually, 1 mole of calcium carbonate contains 100 grams, equivalent to various calcium and magnesium salts present in 1 million parts of mass, 1 million parts by mass of water. So it is expressed in 1 ppm. It may be noted that degree of hardness up to 100 to 150 ppm in water required for our daily needs such as cooking, bathing, washing of clothes, etc. is tolerable. But if it hits more than 100 ppm or 150 ppm, it is not suitable for domestic use. So this is called degree of hardness of water. So calcium carbonate. So in general, it is used to determine the degree of hardness of water. So it's general simple. It is degree of hardness of water. Let us discuss more detail about it. Next, we have preparation of hydrogen peroxide. So before going to hydrogen peroxide, I would like to discuss certain questions based on soft water and hard water. Then we'll start hydrogen peroxide. So let us share. I'll take whiteboard now and we'll discuss certain questions based on soft water and hard water. So let us see now. So I'm taking whiteboard now. So please, this I'll add it now. So now MCQs based on deuterium oxide and water. MCQs on hard water and soft water. Hard water and deuterium oxide. Very, very important MCQs. Then afterwards we'll discuss degree of hardness of water, some numericals. Then we'll discuss hydrogen and its compounds. So let us start now. Questions based on hardness of water. So let us start now. These are very, very important questions. So question number 1, MCQs. Because from this definitely you get one question based on soft water and hard water. Then we'll discuss degree of hardness of water. Then finally we'll do hydrogen compounds, hydrogen peroxide. So question number 1, When? Question number 1, I'm writing. Just please wait 1 second. When a sample of hard water, when a sample of when a sample of hard water, when a sample of hard water is passed through the layer of sodium zeolite, is passed through the layer of sodium zeolite, that is Na2Z, sodium zeolite, resulting which are the following as resulting which of the following ions, which of the following ions, which are the following ions will not be present in the resulting sample of water obtained, will not be present, will not be present in the resulting sample of water obtained, in the resulting sample of water obtained. So option 1 is magnesium ions and calcium ions. Option 2, it is calcium and sodium ions. Option 3, it is magnesium and carbonate ions, magnesium ions and carbonate ions. And option 4, it is carbonate ions and chlorine ions. So this is nothing but simple. The answer is just now we have discussed. It is called, the solution is nothing but Gans permitted process. Gans permitted process, that is sodium orthosilicate, sodium aluminum orthosilicate is called permitted. So in this what happens, Na2Z combines with M plus 2 ions and forms MZ2 MZ2 plus 2 NaCl, 2 Na plus. So this is nothing but what, this Z is called zeolite, and which is removed here, magnesium and calcium ions are removed. So answer is first option. Answer is what? First option. Very, very important. Next question number 2. Let us see now question number 2. Which of the following is not a water softener? Which of the following is not a water softener? So option A, it is calgon. Option B, it is permitted. Option C, it is sodium carbonate. And option D, it is sodium sulfate. So answer straight away you can say it is nothing but sodium sulfate, because permitted is water softener, calgon, sodium carbonate is washing soda, so it is also water softener. Only sodium sulfate is not a water softener. Next question. Question number 3. So all these questions are most important. Both temporary and permanent hardness of water both temporary and permanent hardness of water is removed on boiling with is removed on boiling with option A, it is calcium hydroxide. Option B, it is sodium carbonate. Option C, it is calcium carbonate. And option D, it is calcium oxide. So these are the four options they are given. Very, very important question. Both permanent and temporary hardness have been removed by using sodium carbonate. So answer is what? Sodium carbonate. Because this is used in both temporary hardness and permanent hardness of water. Next question, question number 4. Question number 4 now. Water softening. Water softening by Clark's process. Clark's process. Water softening by Clark's process uses option A, it is calcium bicarbonate, calcium bicarbonate. Option B, it is calcium hydroxide. So by this time you should know the answer. So option B, it is calcium hydroxide. Option C, it is potash alum, potash alum. And option D, it is sodium bicarbonate, sodium bicarbonate. So we already know a calculated amount of lime is added for water softening by Clark's method. So answer is second option, that is calcium hydroxide. So in Clark process, a calculated quantity of lime is added to hard water. Next question, question number 5. So like these questions are most important. So please make a note, children. Next question. The temporary hardness of water. This is previous IIT question. The temporary hardness of water. The temporary hardness of water due to calcium bicarbonate can be removed by adding due to calcium bicarbonate. Calcium bicarbonate can be removed by adding option A, calcium carbonate, option B, calcium hydroxide, option C, calcium chloride, and option D, HCl. So this same question, just the previous question only, but the type of questioning is different. So his answer is option B, that is calcium hydroxide. Next question, question number 6. Heavy water is heavy water is option A, H2O 18, option B, water obtained by repeated distillation, water obtained by repeated distillation, repeated distillation, option C, it is D2O, and option D, it is water at 4 degrees C. Water at 4 degrees C. So H2O molecular weight they have given, so for confusing shape. So it is nothing but answer is simply deuterium oxide, because heavy water is option C, that is deuterium oxide. So deuterium oxide is called heavy water. Deuterium oxide is called what? Heavy water. Next question. Next question is very, very important. So question number 7. Let us see now. This is JEE Mains 1990 question. When zeolite, which is hydrated, sodium aluminum silicate, sodium aluminum orthosilicate, sodium aluminum silicate, comma, is treated with hot water, is treated with hard water. The sodium ions are exchanged with the sodium ions are exchanged. The sodium ions are exchanged with. So it is more than one correct option. H plus ions. Second one, option B, calcium ions. Option C, sulfate ions. Option D, magnesium ions. So sodium ions are getting exchanged with, it is more than one correct option. So straight away easily we can say calcium ions as well as magnesium ions. So answer is B and D. Answer B comma D, because it is more than one correct option. As I told you, this question has come for IIT Advanced. Next question number 8. Let us discuss now. Very, very important. This JEE Main IIT JEE 2002 question. It is also very important question. Please listen carefully now. So I'll write in first page because it is lengthy question. Okay. Pyrophosphates. Pyrophosphates. Nothing but what? Calgons. Pyrophosphate is also called as calgons. Can also call it as calgons. Are used as water softening agents. Water softening agents because they, option 1, option A, form soluble complexes with the anionic species. Form soluble complexes. Soluble complexes with anionic species. With an ionic species. Option B, precipitate anionic species. Precipitates an ionic species. Option C, form soluble complexes with cations. Form soluble complex with cations. And option D, precipitate cationic species. Precipitate cationic species. So they precipitate cationic species. This already we know. So answer for this is option D. because calgon is sodium polymetaphosphate. So polymetaphosphate, that is pyrophosphate, also called as calgons, they precipitate cationic species such as calcium and magnesium. They precipitate cationic species such as calcium and magnesium. So answer is fourth option, that is D. So please make a note, all of you. So these are the important questions. More about this we'll discuss later on. So with this, I'm ending this session. So please follow what we discussed. In this session, we discussed about water, physical properties, and also deuterium oxide preparation, and also removal of hardness of water, both permanent and temporary, and questions based on this. So with this, I am ending this lecture. The next lecture will come up with a new topic. Thank you all.